Okay, so where we left off with the photoelectric effect, where I left you hanging, was with these graphs, with the fact that the intensity doesn't change, the intensity of the light hitting our revamped experiment, the intensity of the light does not change the kinetic energy of the electrons, doesn't change the speed with which they come off, doesn't change the energy with which they come off, but it does change the number of electrons that come off from the earlier part of the earlier apparatus. And the frequency doesn't change the number that comes off, but it changes the kinetic energy. And so then the question is how? So I just redrew it back here so it'd be a little neater. And I have the three different metals. One of the other things that they discovered was that if they extrapolated this line back to where they intercepted the y-axis, they intercepted at a spot that they called WO, where WO was the minimum energy needed to release the electron. The minimum energy needed to release the electron. And again, they could find that from their apparatus, right? They could send different amounts of energy of light in until they finally saw something move in the ammeter to indicate electrons were being. So they know this is a line. We know the equation for a line, y equals mx plus b. And so the plus b part we know is negative WO because it's on the bottom. And the m we know is the same for all of them. This y is the EK max. And on the x is F. So this is F. And we have something that's the slope that we don't know yet. Okay, so that's where we're stuck. That's where we left this. Well, we left it a little bit earlier, but I knew that's where we were going. And we have to pause for a minute, and we have to talk about a guy that you would have heard of in grade 11 chemistry. His name was Maxwell Planck. What they probably didn't tell you in grade 11 chemistry is that he was a physicist. And Maxwell Planck was the guy that suggested that atoms couldn't emit electromagnetic radiation. They couldn't emit energy in a continuous stream. So when an electron was at one energy level and it was going to jump down to another energy level, it couldn't just emit the energy in a continuous stream. It had to emit it as a little packet. Okay? Discrete packets. And this discrete packet of energy is what we call a quantum. A quantum of energy. So quantum is just a tiny little amount, a packet or a quantum of energy. Okay? And the other thing that Maxwell Planck suggested was that we call these packets of energy or quantums of energy, we call them photons. Okay, so a photon is a packet of energy that's being emitted by an electron as an electron falls from a higher energy level to a lower energy level. And I'm thinking you learned that in grade 11, but if not, let me say it again. A photon is simply a packet of energy that is released when an electron falls from a higher level to a lower level. And what Maxwell Planck suggested, and we know it, is that an electron can only release energy in packets. So it's kind of like your faucet, okay? You can turn it on so there's a gush of water, or you can turn it on where it just releases drops. And so Planck's saying the energy can only be released in drops. It can't be a stream of water. It can only be in drops. Okay? Now, a photon of energy, really is electromagnetic radiation or light, and it has both energy and momentum, but it does not have mass. And I know, how can it have momentum and not mass? You're going to have to wait. We'll get there, I promise, but not right now. Okay? And where I think you saw this in chemistry would have been with the equation then the energy of a photon is equal to hf. Okay? So f is the frequency of the light. And of course, from grade 11, frequency is measured in hertz. And E is the energy of the photon. And usually in physics, we measure it in joules. And H is a constant named Planck's constant that I'm pretty sure you would have seen last year. Planck's constant. Okay? And H is equal to 6.626 times 10, I'm going to run out of space here, negative 34 joule seconds. So that when you multiply it by the frequency, you'll be left with just joules. Let me write it over here. My paper was angled. So H is 6.626 times 10 to the negative 34 joule seconds. Okay? It's called Planck's constant, and I think you would have seen it in grade 11 chemistry. All right, so we can figure out then the photon of the energy of a photon. Okay, and remember that we also know that the speed of a photon is c equals f lambda. So we have E equals hf and we have c equals f lambda. So obviously if we know the wavelength, we can find the frequency and we can get the energy. Okay, so that's a little sidetrack, but it's a little sidetrack that's important because Einstein uses what Planck found to describe what's going on in the photoelectric effect. Okay? Einstein suggests that not only can atoms only emit energy in discrete packets, in photons, that they can only absorb them as well in discrete packets. And so when we go back to our apparatus, what he's saying then is this light that's coming in is a whole bunch of packets of energy. And those packets of energy are HF, dependent upon the frequency of the light. And if the frequency of the light is big enough, right? If the frequency of the light is big enough, I need my other picture. If the frequency of the light is big enough, then it'll emit electrons. And those electrons will come off at some speed. But if the frequency is too low, it won't have enough energy to overcome the energy that the material needs to release it. It won't have enough energy to be bigger than the WO. So this energy, this minimum energy that the material needs to release the electrons is really just an E, so it must be equal to H times FO, the minimum frequency. This is called the work function, the minimum energy needed to do the work to release the electron. Okay? Where was my equation? Oh, up here. So that's the WO. The EK max we know is 1/2 kx squared. So what the heck is this? Well, guess what? When we study these lines and they all have the same slope, guess what the slope is? It's Planck's constant. Ta-da! This is actually how we find the value for Planck's constant. This equation is HF. I need a new sheet of paper. So our equation is EK max, the energy that the electrons come off with, is equal to HF minus WO. So this is the kinetic energy of the electron. It's going to run out of time. This is the energy that the photons that are striking the metal have. And this is the energy that the material, the metal, needs in order to release an electron.